Okay, good day everyone. So in this section, we have to discuss the second method. This is the continuous method in finding the roots of a function using numerical methods solutions. So the second method, the background of the second method regards a function that is approximately linear, which passes through the 2 points x1 and x2, and able to determine the roots of a linear function. The interval x1 x2 should not be of opposite sign interval, for which the next values of x does not lie inside the said interval. As a consequence, the residual convergence must be used in this algorithm instead of true convergence. So this figure illustrates the second method. So unlike for the bisection method in which the interval is divided in half, the second method is oftentimes much faster than bisection method, but it does not maintain an interval in which the solution must lie and may fail to converge. So this can also be generalized into two or more dimensions, which is usually called as the Broyden's method. So also this method does not involve the differentiation of a function, but rather use a difference to estimate the slope. Okay, consider this figure I'm presenting. So this is a figure in illustrating the second method. Okay, as you can see, second method always crosses the x-axis. So therefore, what I'm trying to say is, so this is the root of the function. This is always the root of the function. Okay, so we have to draw a line here. So that is crossing the x-axis. So the slope of the slope the slope of a segment or line AC and AE is merely just the same. Okay, if we get the slope of that two point, we use the slope formula, which is m is equal to y sub 2 minus y sub 1 over x2 minus x sub 1. So therefore, if we say the slope at AC, so segment AC, slope of that line, we have a function of xi minus 1 minus 0, because in the point x, in the point A, the coordinates is xi plus 1 and 0. Okay, so x2 here referring to xi minus 1 minus xi plus 1. Okay, so that slope of AC is similarly equal to the slope of AE, or the segment line AE. So we have a two similar triangles here in our figure. As you can see, we have triangle ABC, which is this, and also the triangle ADE. So for similar triangles, the height is proportional to width. So considering that there are similar triangles, the triangle ABC and also triangle ADE. So there are similar triangles. So for similar triangles, so the height is proportional to the width. Okay, so we have a ratio of their the height and the width. So we have considered the segment DE over segment VC. So this is proportional to segment AD and segment AB. Now, the segment DE, that is, if you get the height of segment DE, this is equal to F xi. So F xi. Okay. Segment BC, I'm referring to F of xi minus 1. This is equal to segment AD. Segment AD is this particular width of the triangle. So therefore, we have to get xi minus xi plus 1. And also for segment AB, which is this one, this is xi minus 1 minus xi plus 1. Okay, and then we'll cross multiply this two left hand side equations, the left hand side equation and the right hand side equation. So if we cross multiply this one, we have say begin with the left hand side equation. We have f of xi, multiply that by xi minus 1 minus xi plus 1. So this is equal to the right hand side equation, that is f of xi minus 1 times xi minus xi plus 1. So if we derive this, this is the derivation of the formula of the secant method. So let us continue. Okay. So we will arrive for this formula. Let me erase this one. Okay. So the formula of the secant method, as if we have to do a derivation of what we have in the proportionality of the height equal to the width of the proportional triangle, this is the formula of the secant method. We have xi plus 1 equal to xi minus f of xi f of xi multiply by xi minus xi minus 1. So this is all over f of xi minus f of xi minus 1. So this is the formula of the secant method. So usually the iteration will start at I equal to 0. Okay, so at I is 0, so therefore you can get the next iteration, which is x1 equal to x0, because I is 0, minus f of x0, multiply that by x0 minus x of negative 1, f of x0 minus f of x negative 1. But usually uh, x1 in secant method is initially given. So x1 is initially given, should be uh, given. So usually you will start at, so x1 is given, so therefore if you have x1 you will start at I equal to 1. So usually in secant method x1 and x0 is already given, because that is the two interval that we are finding, because the root is between those two interval. Okay, let's have some example. Let us have some example in secant method. Okay, so example, find the roots of the function. Find Okay, let me write. Okay, so find the roots of the function f of x equal to x cubed minus 20 by secant method. By secant up to 3 decimal places. So we have initial approximations of, we have to use initial approximations at x0 equal to 3 and x1 equal to 5. So what we have to do is to solve for, first is, we all know that the formula is xi plus 1 equal to xi minus f of xi minus xi minus 1, also over f of xi minus f of xi minus 1. Okay, so let's start by solving the f of x0. So if we solve for f of x0, say f of x0, so that is, I'm referring to f of 3. So therefore that if f of 3 or f of 0, so you need to substitute this to the function. Say this is 3 cube minus 20. So therefore, if this is now the function of x0 at f of 3, we have 27 minus 20, we have 7. Okay, so for f of x1, say f of x1, so therefore that is f of 5. Okay, so for f of 5, that we have 5 to the cube minus 20, so we have 25. Sorry, this is 105 because 125 125 minus 20, this is 105. Okay, so we have those possible values, or we get the values of f of 0 and f of x1, so we need to substitute that uh, to this formula. So I need to say that already x of 0 and x1 is given, so therefore we have to get the next iteration, which is the x, we have here the, so we'll start at I is equal to 1. So we'll start with I is equal to 1. So therefore we have to get x2. So x2 is x1 minus f of x1 times x1 minus x0. So this is all over f of x1 minus f of x0. So therefore, if we have to substitute x1, the values of x1 is 5. So minus, we have already get the values of fx1, which is 105. Multiply that by x1 minus x0. So therefore, this is 5 minus 3. So f of x1 is 105, and the values of f of 0 is 7. So therefore we have get the value of, we have x2, that is 20 over 7. Okay, so we'll continue again, so by solving f of x2. So f of x2 is, we have to substitute that the values that we have get, which is 20 over 7, to our function. So our function is 20 over 7 cube minus 20. So therefore, we can get the values of x2, which equal to 1140 over 343, or this is equal to, in decimal, 3.3236. Okay, so let us continue. So if we solve for f of x2 again, we can solve for x of 3. So our x of 3 is, so meaning the next iteration would be I equal to 2. So I equal to 2. So for the next iteration would be this will be now x3. So our x2 is 20 over 7 minus f of x2. We have 3.3236. Multiply that by the values of x2 minus x1. So our x2 is 20 over 7 minus x1, which is 5. Okay, over 3.3236 minus 105, which is the value of f of x1. So therefore, the value of x3 is 432 over 155, or this is equal to 2.787096774. Okay. Also, you can get the error of the x1, x2, and x3 using the following formula. We have this error, absolute value of error, this x2 minus x1 over x2 times 100, and also get a value of the error, which is equal to, for x2 minus x1 we have 75%. So as you can see, the error is very large. Okay, so the result of x3 we have to substitute. So f of x3 is 1.649912524. So the value of our x3, as earlier we have solved, is 2.787096774. So we get, for function of x3, we have get 1.649912524. So using the function of x equal to x cubed minus 20. So if we have to solve again for the error of our difference between x3 minus x2 over x3 times 100, we have approximately equal error of 2.51%. Okay, we have the error. Okay. So again, let us continue by solving x4. So by solving x4, we have so we are now in the I equal to 3. So we have x4 is equal to x3 minus f of x3 times x3 minus x2 over f of x3 minus f of x2. So we have this formula. Okay. So getting x4 by using or by substituting the values of x3, f of x3, x3, and x2, and f of x2, we have the value of x4 is 2.71 2.718046331. So that is the value of our x4. Now we have to evaluate the value of fx4. Oh, so that is f of 2.718 into our original function, which is x cubed minus 20, and then we get 0.080317. Okay, so again, if we get the error, the absolute error is equal to absolute value of x4 minus x3 over x4 times 100, we get the value of 2.54%. Okay, so we will continue at uh, iteration at I equal to 4, or that is, we can get the value of x5. So therefore, at I equal to 4, we have, or the next iteration will be x5. So our x5 will be x4 minus f of x4, x4 minus x3, all over f of x4 minus f of x3. Then again, class, we have already find the values of these x4, x3, and also the f of x4. So we can get for x5. So the value of x5 is 2.714512982. Okay, let us continue. So solving also f of x5, we have this f of 2.7145. So that is equal to 2.108 times 10 to the minus 3. So again, if you compute for the error, we have absolute value of the error. It is equal to x5 minus x4 over x5 times 100. So as you can see that the error is now at 0.13%. Okay, so let us continue to reduce the error minimal to this. We have get as 0.13% as the difference between x5 and x4. So let's continue at I equal to 5. So at I equal to 5, we are expecting that we have to solve x6. So at I equal to 5, we have x6 equal to x5 minus f of x5 times x5 minus x4. So this is all over f of x5 minus f of x4. So again, we have solved already the values of x5, x4, and also f of x5 as presented earlier in the solution. So our value of x6 is 2.714417744. Okay, so we can say that x6, or this value of 2.714417744, is the root of function, since x5 and x6 have been repeated up to 3 decimal places. So our value of x5 as earlier as solved is 2.7145. So as you compare repeated three decimal places as we solve for the value of x6. So therefore, you can say that we have found the root. Okay. So this function also can be graphed uh, using MATLAB software. So since we have function of x equal to x cubed minus 20, we're expecting that this function has three roots because this is polynomial degree of 3. Uh, what we found is the first root, which is the real root of this function, which is 2.7144177744. So this is the real root. Now, the other roots are these are verified in the MATLAB. These are complex conjugate pairs. So for finding a root using the graphical approach, you should graph also using MATLAB or other MATCAD software, and you can also say that the root always lies on the x-axis, and which always consider f of x equals 0. Therefore, we find the real root, which is our ultimate goal is f of x 0. So if we substitute this root to the function, which is f of 2.7144, this is cube minus 20. So we're expecting that the function would be 0. Okay, so that's the end of the second method, and thank you for listening, and we'll continue this on the next uh, numerical method solution, which is the fixed point iteration method. Thank you very much, everyone.